Okay. Welcome to the crypto seminar, everyone. Today we have Alex. He will be presenting his work on Plinko, single server PIR with efficient updates via invertible PRFs. This is his joint work with Server, Giuseppe, and Kevin. Let's welcome.
Thanks. Yeah, so like you said, I'll be talking about Plinko. This is a recent eFriend that we put up. You can probably do that link. If there are any questions at all throughout the talk, feel free to interrupt. It's not a super long talk, and I'd rather people understand what's on the slides than anything else. I don't have my presenter notes, so hopefully I remember everything. That's just a disclaimer. Okay, without further ado, let's get into what I'll be talking about. So here's kind of the outline. I'll just first start with like some preliminaries, talk about what PIR is, what preprocessing is, and then I'll recall the definition of PRFs and PRPs, because we're going to build an invertible PRF later. And then I'll talk about some prior work, and then I'll talk about how we pretty much directly work off of prior work and improve it in specific ways. And then sections 3 and 4 will be the bulk of what's novel in the paper. Okay, so let's jump in to what information retrieval is. So there's no cryptography going on here. This is just information retrieval. So the setting we care about is where a client is interested in learning a specific element of an array that I'll call a database. So in a setting where they don't care about privacy, they can just send the element index X to the server holding the database. There's no encryption going on. It's publicly accessible information. And then the database can just send back the relevant information. So you can think of this as like a DNS lookup, or like accessing stock information, or just accessing a web page from some public web service, or like maybe some public database, like a voter registration. However, if a client wishes to avoid revealing what element they're interested in, maybe they don't want you
excuse me, actually we cannot hear the speaker. The voice is very faint.
Okay. You can move that and unmute here.
No, probably Alex should try audio.
Yeah.
No, but recording does not capture the audio.
Wait, really? I think it should, but
Okay.
okay, is this better?
Yeah, it's better.
Okay, then maybe we can just keep it like this. It's okay.
Okay, speak up if it's still bad, and we can, I guess, try something else. But yes, if a client doesn't want to reveal the specific information they're interested in, like maybe I don't want you knowing which stock I'm looking up, we can use a tool called private information retrieval, which was introduced in the 90s. And here the client and the server engage in some protocol. And at the end of the protocol, the client should learn the information that they're interested in, DB at X, and the server should have no idea what index the client is interested in. And here, when I say that the server learns nothing about the queried index, I mean in a computational sense, for those who know what that means.
Actually, do you mind moving the microphone closer to you? Because I think with this, the recording quality will still be very bad. The voice will be hard to hear.
Maybe
I think we should use his own microphone instead of yours.
Okay.
Okay, now I'm using.
Or you can also have the speaker zoom in, so he can use his like personal laptop to record the voice.
Just move the left way so there's no
Yeah, you can.
Okay, I am on my, wait, you turned my speaker off? Oh,
No, yours is on.
oh, I can turn my speaker on as well. Okay, there we go. Now I'm using my personal laptop. Hopefully this records better.
Yeah, this is.
Okay, great. So yes, the client. So unfortunately, as written here, we already run into like an efficiency bottleneck. For a protocol like this to be truly private, the server is going to have to read its entire database every time that the client issues a query. You can see this because if there's any like element of the database that the server didn't touch when it's running the protocol, then they can infer that the client was not interested in that specific element, and that violates our privacy that we want. Okay, so one solution to try to get around this efficiency bottleneck is preprocessing. Specifically, I'll talk about client-side preprocessing. So here, We let the client interact with the server in an offline phase, and they engage in some offline protocol. This is before the client knows the index that they're interested in. And then in the online phase later, the client will learn or know what index they're interested in, and they can use this set of hints or this small bit of data that they've computed in the offline phase to perform an online query. Hopefully this online query is a lot faster than in the traditional PIR setting. And this is something that was introduced in 2000 and then kind of reintroduced in like 2018 and 19. So efficiency in the setting, in the offline phase, we still have to incur like a linear computation. The server is going to be able to read everything. And in particular, what we'll talk about is we'll have the server actually just send the entire database to the client in a streaming fashion. And then in the online phase, the hope is that we achieve sublinear computation, both between the client and the server. So maybe it's like square root in, you can think about. Unfortunately, in this setting, as I've drawn it, it introduces a problem that wasn't present in the normal PIR setting. Specifically, what happens if the database changes between the offline and the online phase. Because I've done this pre-computation, I have this small set of hints. And this set of hints depends on the data in the database. And so if I change the data in the database at all, it's not clear at all. It's not clear what I can do with my hints, whether I can do an online query or whether I have to like update them somehow. So that's what we're focusing on in this work. Okay. Briefly, I'll just mention like kind of the idea on how we update hints. So we're going to focus on this type of update, where if an element updates from dbx to dbx prime, then the server will just push out an update to the client. They'll say, I updated this entry from this value to this value. And then we leave it on the client. The client is either going to have to update their hints to be consistent with the new database. It's not a priori clear that they can do that. It turns out that they can. Or we're going to have the client store the hints. We're going to talk about why they don't want to store it on the next slide. And all the work before our work would require the client to do a full pass over their local storage in order to remain consistent with the database. There are other approaches like Bentley-Sachs that avoid this type of client computation, and the protocol is not as simple as just sending the update. I won't go into them here, but they are interesting in their own right. But after our work, asymptotically at least, we beat Bentley-Sachs on all the measures that you want to.
Okay. Can you do lazy updating? Or you just store
like this?
Updated in?
It's a good question. Yeah, so if I just store.
Do you mind repeating the question? We cannot hear the question remote.
Oh, yeah. Sorry, the question was whether you can do lazy updates. Like, can I just store the updates? And so I'll talk about this on this slide. What you do, like maybe the client doesn't want to pass through their hints and they just store the updates that the server is sending them. So this solution does work if you have very few hints, because it turns out you can like process the query and then you can scan through the hints that you've stored and you can kind of correct the query afterward. That's just a property of how these schemes work. Unfortunately, in a setting where you have many hints, this achieves the same type of asymptotics as the other solution where you do the full pass over the hints. Specifically, we think of the client as having like square root in, where in is the database side square root in storage. And so they may only be able to store square root in hints. And after square root in hints, you'd have to rerun the offline phase and get a new set of hints back. And so it amortizes out to like square root in, which is the same as the previous setting for typical parameters. Okay, instead, we're going to try to improve this exponentially to polylog time. Okay. And then this is just unrelated to PIR a little bit, but just to remind everyone what a PRF and what a PRP is. A pseudorandom function is a keyed function that takes as input into an adversary who can query it is indistinguishable from a random function. And a PRP is something that's indistinguishable from a random permutation. And what's key about a PRP is that it has an efficient forward and backward oracle, and it's still indistinguishable. And it uses the same key. Okay, we're not going to worry about like public key variants of these primitives. So that's kind of preliminary. Now I'll talk about a bit more how specifically two works achieve PIR with preprocessing. Okay. So the two works that I have in mind are Piano and MIR. So Piano is the name of a scheme by people here at CMU. It's a great scheme. And MIR is a scheme by, I think, people at UIUC. They both have a common structure, though. And so what we do, our novel improvements, can be applied to either one. And specifically, what they haven't, I'll focus on what they haven't.
Can I ask a question?
Yes, please.
Does MIR stand for mysterious information retrieval?
It's a great question. No, those are the first, those are the author's first or last names, the first letter of the author's last name. So Mugi's I and Ren. But they should have named their scheme MIR if that didn't de-anonymize it. Yeah, so both of them, both Piano and MIR, have the structure where they view the database as separated into B blocks, each of width W. So you can think of every time I say B or W, you can plug in, square it in, but I'll keep them as B and W because they do trade off, and we'll talk about that at the end maybe. And so a set in both of these schemes, or the relevant part of the hint that I'll call a set, consists of one element from each block. So if I say a random set throughout the talk, it's going to be talking about picking an offset for B blocks. So a set is fully specified by B offsets, each an integer between 0 and W minus 1. Okay, and if you order those offsets, that just tells you the elements of the database that are in the set. Okay, and sometimes I'll write an index X as T comma S, just because that's notationally convenient. So it's in block T at offset S. Okay. So the hint structure, so here, I'll talk about the relevant aspects of the hint structure. Both the schemes have a little bit more going on, but this is all that's really like core to what we improve on. Both have like a set and they have a parity. This is a bit closer to the hints in the original version of Piano, but a set is just going to be represented as a key. So I have a PRF key, and then that defines a set because I can just feed into my PRF 1, 2, 3, all the way up to B. And the outputs of that PRF are going to give me integers between 0 and W minus 1. And so if I have B of these offsets, like I said, that just specifies a set. And so a hint consists of a set and then together with a parity. And this parity is going to be the sum of the database elements of that set. Okay. So if there's anything confusing here or about the hint structure going forward, please ask, because like this is kind of where the improvements are going to come. Yeah.
So the elements are supposed to be bits or field or words or something, or does it matter?
They can be bit strings. So yeah, this will be an XOR. They could be field elements in general, I think. I don't think there's any issue with that, but they're just bit strings. So usually it's 0 or 1, 0 and 1. Okay. And we have the client store lambda W of these. So it has to be proportional to the block width. And that's so that every single element appears in at least one hint. And that's important so that we can query the elements. Okay. I just added this slide because a detail I'm going to elide throughout the talk are called backup hints for people familiar with these schemes. If you're not familiar, you can kind of ignore what I'm saying on this slide. But basically, it's critical to have backup hints because after you do a query in these schemes, you consume the hint. It cannot be used anymore for privacy. And so you have to find a way to replenish the hints. It turns out that our techniques, we can do this, but it kind of complicates a lot of the conceptual stuff that's going on. Just know it doesn't drastically increase the client overhead, and it is something that is critical to actually make these schemes work. Okay.
Actually, I want to say it's not critical because in our new paper, we have a technique called broken hint, and we don't need these backup hints anymore.
Oh yeah, I did read this paper. Yeah, okay. So it's not critical. It's critical to Piano and MIR. Let's go with that. I think that's true. Anyway, we can handle backup hints. I don't know if we could do broken hints. So I'll just go over kind of how Piano works for people who aren't familiar, just so you have an idea of how these hints are used. Although what we're going to focus on in the talk are the updates. So the offline and online phases are not super important to the core of the talk. But basically, the way that Piano works is that we stream each of the B blocks one at a time. So we download a block, and then we iterate through all of our hints, and we run the PRF with the relevant key for that hint to find the offset for the whatever block that we're on. And then we go and grab that element, and we add it onto the parity. Right, so after we've downloaded the first block and scanned through our hint, all the parities have been like, they've all had their first element added on. And then by the time we're done with the Bth block, all the parities are correctly computed and initialized, I'll say, and ready to be used for a query. Okay. And then in the offline phase, what we do is to query a specific element X that's at T comma S. We first find a hint that contains X. This is just by linearly scanning through the hints. And then our goal is going to be to find the parity of every element in that set except for S. If we find the sum of all those elements, then we can just subtract it off of the parity we have stored, and we'll get out exactly the database element that we want. Okay, so what this looks like is we remove, this is the original version of Piano. I understand there have been updates since, but we remove the offset that corresponds to X, and we send the remaining offsets to the server. So there are B-1 ordered offsets. The server has no idea which one we've removed. What the server does is it basically guesses which one we've removed. So it kind of assumes that we removed the first one and it sends the parities back for the remaining. And then it assumes we removed the second and it sends back the parities for the remaining and so on. And it sends back B ordered parities. And we just pick out the parity that corresponds to the correct guess, right? So the one where OT really was removed. And then we can just subtract off the parity that we were storing and get back exactly the database element that we're interested in. Okay, that's how Piano works at a very high level for a single query. Updates in both Piano and MIR work in the following way. Under our scheme, so you could use Bentley Sachs, but we're going to elide those details. So if I tell you that I've updated element X at dbx, or from dbx to dbx prime, I iterate through every hint. I check if X is in the hint set via this PRF computation. If it is, then I subtract off the old value and add on the new value. And at the end of this loop, through all the hints, my hints are still going to be consistent with the database. Okay, unfortunately, this requires like OW time, because remember the client is storing lambda W hints. And our goal is going to be to avoid this pass over all of the hints and get it down to polylog. So I'll talk about how we do that in the next section. If there are any questions, please ask now. I'll just take a sip of water.
Yes, so just to make sure I understand, so you want to like have the client do when there's an update, the client computation, you want it to be polylog. Is that the goal?
That's exactly right. Yeah.
I see. So basically the problem is like in Piano, if you receive an update, you would have to scan through the table, and it takes square root n time to update your hint table.
Yes.
Okay. I see. I think I understand the problem now.
Okay, great. Yeah. And both, I think all the schemes before our scheme required this pass through every hint. So like this is how you would handle hints if this is how you wanted to do updates. You could do something like Bentley Sachs and cut down the client computation, but that introduces other complexities.
I guess there's another way to do update. That is, you just store those updates. You don't update, you don't like change original hint, but whenever you expand those hints, whenever you touch like one particular index, you just do like a set membership check on those like stored updates. And if you see an update, you just change the current value.
So the client is
Oh, but that doesn't work. Okay.
happy to talk more about it later. Yeah. Then there are a few ways you could try to think about it, but yeah, the trivial way definitely requires passing over things. You could try to like delay the hints, you could store them and then try to process them later. Every way that I can like conceive of that is going to like amortize out to asymptotically the same behavior.
Also, is your technique compatible with Bentley Sachs? Because I feel like eventually, like with the stuff dimension is saying, eventually it'll just become something like Bentley Sachs, right? Because you don't want to start the table, the update table will be linear, it can be linear in size. So like if we develop our mission's idea, it'll just become some Bentley Sachs.
So our technique that we do, like you could definitely still do Bentley Sachs on top of it as far as I know, but we're not going to require any additional storage in our scheme. So like, I guess I don't know the benefit of doing Bentley Sachs. Once we have, maybe this will be answered later when I talk about how we achieve the polylog, but like we're not incurring extra storage in our scheme versus Piano and MIR. So let me talk a little bit about how
But
we're going.
are you saying boundless X is strictly worse than your scheme, or?
Yes.
I see.
Maybe the asymptotics will be clearer after the scheme. And we can talk about it afterward too. Okay, so what is our goal? Our goal is to get an efficient hint finding algorithm. All right, so we want to avoid this check where we pass through every single hint and run this PRF. Ideally, we only are going to touch the hints that contain a specific element X after X is updated. Okay, that's the goal. Unfortunately, the way that the hints are structured right now, it seems kind of unachievable unless this PRF has very weird properties, because these keys are completely independent of one another. Each one is just like a random bit string that you generated with some key derivation function. And so it's not clear, like given this set of like keys, how you're going to find just the hints that contain the element that you're interested in. And so kind of the first insight that we have is to view all of these hints as kind of like one big data structure, and to change what I call the hint structure. We're going to change how we're computing the offsets. Okay. So the first change that we do is we change how we use the keys. So before, each of the hints had its own independent key. And now we're going to have a key per block. Okay, so we kind of turn it on its side. And a hint is going to have a specific index assigned to it. And so like all I'm doing on the slide is flipping the T and the J. But what this amounts to is that every block has a key. And then every hint has an index. And so you just run F of the block key at the hint index, and that gives you the offset. So the distribution of these offsets is still just uniform. I can still enumerate these offsets efficiently. So just making this change, you could still run Piano and MIR as is, but we haven't gotten an efficient hint finding algorithm yet.
So you're just changing like from row generation to column generation, is that?
Yeah. So these are block keys. So now a key is assigned to a block rather than to a hint. Okay, so like this, it's still a PRF, so these offsets appear uniform and independent, but now they're at least using the same key, and we're gonna exploit that. So like within the same block, they're using the same key. Okay. So the first attempt that we're going to do, this isn't going to work, is we're going to get efficient hint searching, but we're going to break the PIR, which is, half the battle. So to update a specific element X, right now we have to run this PRF for the block key to check if it is with the specific offset. But the first thing we do is we substitute the PRF with a PRP. So now each of these columns you can think of as just having the element 0 to W minus 1 permuted. Each one is an independent permutation, and we're using a PRP. And what the nice thing about a PRP, if you'll recall, it has an efficient inversion function. So if we did this, then we actually do get efficient hint finding. If you tell me the block and the offset for an element X, then I can just run PRP inverse with the block key at offset S, and that'll give me back exactly the hint that has X in it. Now, this, like I said, this breaks the PIR scheme, so let's talk about that. So unfortunately, if you use a PIR permutation, these hints are no longer uniformly random offsets, right? There are weird correlations between the hints. Specifically, no column is ever going to have a repeating offset. And that's actually going to break the security of the scheme. It's also not clear how to adapt like backups to this setting. There are a few problems that arise, but critically, it's not ever going to be private because we're using a small domain PRP. And these are just distinguishable from random functions. In fact, even truncated permutations, for those of you who know what that is, aren't going to work. So that's like where you blow up the domain and the range size and kind of mod down to kind of force yourself to have some collisions. Even these are distinguishable from random functions on small domains. So we need something different. In fact, what we need is an invertible PRF, as the title of the talk may have suggested. So what we need is a PRF that has that's a pair of keyed functions where the forward direction is like a normal PRF. Okay, so it's indistinguishable from a random function. Everything looks uniform and independent. But then it also has an efficient inversion function. So if I give you the key, then you can find me the pre-image set of any output. Okay, if I have this, then we're good. We're going to have the security that we need because all the offsets will appear uniform and independent, and we'll have the efficiency because we can do this inversion. Let's show you on the next slide how we do that. And I have this asterisk because technically our application here only needs a weaker type of security than I've drawn in this picture, but the definition makes sense for the picture drawn. Okay. So once we have such a thing, then we just instantiate an IPRF from lambda w, so the number of hints, the hint indices, to the size of the blocks. And then each offset is uniformly and independently distributed like we want. So we have the privacy of the scheme. And additionally, now we can find hints efficiently. All we have to do is we just invert. So if you just want to find x at TS, we just invert the PRF under key KT at S, and we get back a set. And this will be all of the hints that contain the element X. Okay. So this is awesome. We've pretty much solved the problem. So now recall how we did updates in piano and MIR. We did this linear scan, required O lambda W time. And now updates in Plinko is just a really simple pseudocode. And now we're only doing a for loop over the pre-image set. We just run the F inverse. We just loop over only those PJs. And these pre-images are going to be concentrated with high probability. All of these pre-images are going to be like logarithmic size. And so now we have what we want. We have polylog time updates. So this is great. There is one problem, is that invertible PRFs don't exist. At least they didn't prior to our work. And there is an asterisk here because technically invertible PRFs did exist for large domains because of PRP is one such invertible PRF. But for small domains, which is what we want, right? We want square root size, very small domains. All right. So now I'll talk about, just in the last part of the talk, how we build an invertible PRF. I'm pretty much done with the PIR stuff, so that if there are any questions about that, feel free to ask.
Yeah, I guess this invertible PRF itself seems like for small domain, seems like a very interesting primitive. I wonder if there are some other applications.
I also wonder that. We did not find any in time for the paper, but I was also just kind of surprised that it hadn't been defined as far as we could tell, like in searching through a bunch of literature, because it seems like a very natural primitive to define. So I don't know all the applications, but happy to think about it. But let's see how we construct one, shall we? So the first step when we're trying to build an invertible PRF is to ask ourselves what a random function is. So we're going to build a random function from a domain of size n to a range of size m. And we're going to view this as just throwing n labeled balls into m labeled bins. Right? So if I have labeled balls and I throw them into bins, then I can just think of the forward direction, f of x, as the bin y containing ball x. So if I ask you, hey, what bin did ball 7 land in? That is f of 7. Okay. And the F inverse is just enumerating all the balls in the specific bin. Okay, if we can efficiently find the bin for each ball and the ball for each bin, then we're going to be done. So that's the goal. Okay. So it turns out that although PRPs didn't solve the problem for PIR, they can be very helpful when we're building an invertible PRF. Specifically, a permutation provides an invertible random labeling, which is going to reduce our problem to just sampling a simpler distribution. So before I told you we're throwing labeled balls into labeled bins, but it turns out that throwing unlabeled balls with a PRP is enough to get an invertible PRF. So imagine you have a bunch of unlabeled balls, you throw them into bins randomly, and then I just like order the bins and I lay out the balls and like put little dividers between all like where the bins capacities were, and I just label them 0 up to n, and then I apply a random permutation to the labels, and those are their new labels. I claim that that distribution is the same as if you had labeled them first and then thrown them randomly. That's what we're doing here. Okay, so if we have a permutation, specifically small domain permutations do exist, then we can simplify our problem to just making sure that we can sample the bins efficiently for any labeling. We don't have to care about the labeling because we can slap a PRP on the end and get our IPRF. So we're going to focus on this multinomial distribution and sampling that efficiently.
So hold on, so you wrote the two formulas there, like fx and f negative y. So that's built upon you already throw unlabeled balls into bins, right?
Yeah.
So how do you define fx here? Because like without throwing the ball first, you just get like a well.
So I'll claim that if you can, so if you throw the ball, like let's say you throw unlabeled balls, right? And then you label them however you want after, like, it doesn't matter how you labeled them. My example was I just numbered them, right? I listed them. But then no matter how you label them, I can apply a PRP, and that's going to be a random labeling.
So basically, after you throw them, you label them 1 to n, and then like basically, you want to know which bin it is in. Like you have some kind of cumulative sum so far, and you just looking to which bin it is in, something like that, and then you compute the inverse PRP to something like that.
Yeah, something like that. So like, I lay them out, right? So I have balls there. Let's say you label them 1 to n, and then the one you label 5 is in bin 3. Then I'll apply a PRP to that, and maybe the output's 20, and I'll say ball 20 landed in bin 3. Okay, so that's what I'm writing here. So bin 3 contains ball with my labeling after applying the PRP. Similarly, if like I can unlabel my ball, so the PRP works both ways, and so I can unlabel my ball and get back to your distribution or your labeling.
So you start with like a black Sharpie, which is mine, and then you use a red Sharpie, which is yours.
Mhm.
All the balls have to black and red, just like which.
Yeah, and if I'm using a PRP after your black Sharpie, I claim it'll have the same distribution as if I had just red Sharpied and then thread. Okay. I think it might become more clear. Well, we'll see if it gets more clear, and if not, feel free to stop me. Okay, but we're going to focus on sampling this multinomial distribution. So specifically the multinomial distribution I'll write is like x0 to xm minus 1. These are going to be the sizes of the bins. What we need is 2 key evaluations. So I need, given a specific bin or ball, which bin is it in? So I'm going to call this like a ball to bin evaluation. And given a specific bin, I'm going to need to be able to list all the balls, right? So these are the same evaluations we wanted for the IPRF, but now I don't care about the labeling. All I care about is that the sizes match the multinomial distribution. Okay. So the way that we do this is we kind of turn to some intuition, some very loose intuition based on this Plinko game that we named the paper after, where in Plinko, we kind of visualize like when you drop a ball on a peg, it goes left or right with probability 1/2. And so if you drop in balls on the same peg, the left is like binomially distributed, but like in 1/2, and the right is similarly distributed. And so this intuition kind of gives us a recursive algorithm for the multinomial distribution. I'll visualize it on the next slide, but this is the pseudocode for it, where, so on line 3, you can see we're sampling a binomial. So I basically am just asking how many balls land in the first half of the bins. That's what L is. And so I sample a binomial and I say, okay, balls 0 through L are in the first half, and the remaining ones are in the right half. And then I just recurse, right? I recurse on the both halves. I have L on the left and R on the right, and I just sample those respectively.
It's kind of not Plinko, right? Because
It's not
Plinko,
Plinko.
when it dropped down to like some
Loose intuition, loose intuition. Yes, it's yes. This is not doing. Yeah, we're gonna get a tree, right? But yeah, it's the binomial. Maybe the name's not the best, but so the idea. Yeah, so now if I'm throwing 30 balls into 8 bins, here's an example run where like I sample 18 at the top node, and then I say like, okay, balls 0 through 17 go to the left, and 18 and up go to the right. And similarly, I just do this for every single node, and I get these labelings. And I'm keeping track of these start indices just so that when I say ball 7, I know what I'm talking about. So this distribution we get at the end is effectively the same as what I said, where I'm throwing unlabeled balls, and then at the end I label them 0 up to n minus 1. Okay, that's what's going on here. So What this means is like, for example, in bin 6, the first ball is 24 and there are 2 balls. So bin 6 contains balls 24 and 25, I would say. Okay. So this is useful because it's going to give us our efficient ball to bin and bin to balls algorithms. So just to run along with an example, if we want to know which bin ball 15 landed in, I'm going to sample my binomial. Ball 15, we know that 0 through 17 went to the left, so we go to the left, sample another binomial. 15 is bigger than 7. Again, 15 is bigger than 13, and so we know ball 15 ended up in bin 3. Similarly, the bin to balls algorithm is pretty much the exact same. If we want to know which balls are in bin 5, all we have to do is follow the path to bin 5. So bin 5 is on the right, we sample our binomial, we go to the right, we sample that binomial, and then we go to the left, and so on. So bin 5 starts at 21 and contains 3 balls. And so we'll say that it contains balls 21, 22, and 23. Okay, so this is great. We have a multinomial algorithm. The reason it's efficient is that it only ever enumerates a single path, right? We're only going down one path. Each path is only log n binomial distributions. Each binomial can be sampled with only log n bits of randomness, it turns out. There's an algorithm for that. And we can easily reproduce these samples with like a PRG or a PRF, because we only care about like computational security here. And so overall, our multinomial sampler just runs in polylog in an m time. And this works for any domain size in an m, large or small. And I have this asterisk because technically if you enumerate the bins and you throw many balls into very few bins, then your pre-image size will be very big. And you do have to, if you're going to print out the whole thing, it'll take that much time.
So here, do you need to require like n and m to be like a power of 2 or no?
No. So if we go back to like here, I just bias the 1/2 according to the number of bins on the left versus the number of bins on the right. On line 3.
Wait, if it's not a power of 2, wouldn't that buy it?
This would be like 13, you might go to these.
Yeah, you could have the tree in any structure.
Oh,
We would
sure.
balance
I
it.
guess like you kind of,
We would
yeah, I guess
balance.
it's doable.
Yeah, it just changes the probability, right? Like if I ask how many like no matter how many bins I have on the left, they're binomially distributed. The sum of them is
Okay.
binomially distributed. And it's just optimal to do like the log.
So can you do it without the PRP, or you need to, because you said you have an algorithm that's log n update time.
Without the PRP?
But is the log n, are you counting PRP cost as O1, or because PRP, small domain PRP has like polylog cost, right? It's not just log n.
Yeah, so it would still be, I'm only claiming that we get polylog time. I'm not saying that we're getting logarithmic time. But the PRP cost at the very end. So this is efficiency of sampling the multinomial distribution. This is not I'm not claiming efficiency of the full IPRF. Has this. Okay. The IPRF is just the natural construction that we outlined before. So in the paper, we define a pseudorandom multinomial sampler, which is what I've pretty much gone through. It's this recursive algorithm with this pair key to functions that correspond to the ball to bin and bin to balls algorithms. And then we just get this IPRF by composing in the way that I said before. We just compose in the correct order and we get out an IPRF. And so this will be like polylog time for some other polynomial, but it'll still be polylog.
Or should we stare at this page?
You don't have to stare. If you got the intuition, then like this is just doing the composition, right? This S is just doing it's just doing ball to bins. S is just ball to bins, and S inverse is just bin to balls. It's just the notation we use in the paper. Yeah. So that's pretty much it. The kind of summary of what we do in the paper. Like I said, we improve the update efficiency. That's what I've been focused on. But another claim is that we are the first work to achieve an optimal trade-off between client storage and query time for all client storages. So prior work from Kevin showed that like R times T for these client storage and what total query time has to be at least N. And this was only previously matched for R less than squared N. And the reason for this is because all the prior works required this linear pass over the client hints. which, so if the client storage was larger, then that kind of killed their trade-off. Okay. We also introduced this definition construction for an IPRF, and it works for every domain size. Unfortunately, our work only applies to like piano and MIR and like related structures. Anything that is using puncturing or a different type of set structure, it's not clear how to get efficient updates. And I think that's a really interesting future work question.
Sorry, I'm still confused about this optimal trade-off. Are you saying you got rid of the log factor? Like the previous work was also kind of optimal, right?
So previous work, no, I'm not claiming that we got rid of the log factor. I'm claiming that previous work did not achieve this trade-off for R bigger than square root n. So if you're familiar with the bound, what it shows is that client storage times server time is at least n up to log factors or something. And everyone meets that bound, or many works meet that bound. What they don't meet is the total query. So what Kevin's bound immediately implies is the exact same trade-off for total query time when you include the client and the server together.
Wait, are you saying in the presence of updates, or because the other previous papers, the total query time should also be tight. The client.
So he's basically saying that if you have to find a hint, like one hint by one hint, that costs a little bit more.
Yeah.
Isn't that like square root n time, and we have square root n storage, so it's right?
Block size.
So imagine you have the client is storing into the 2/3 hints, right? So we don't pick into the 1/2. If the client has into the 2/3 hints, then the blocks are going to be into the 1/3 width. Okay. And the client, though, when they try to find a hint that contains their element, that contains their query, they're going to have to scan through about into the 2/3 things before they find a hint that contains the element they're interested in.
Oh, I see. For large client size storage.
Precisely.
That makes sense.
Yeah. So we're the first for clients with large storage. We achieve this trade-off optimally. There is technically nothing ruling out, like a client could have constant time, and Kevin's bound doesn't like prevent that. So it is possible to improve the client time even further beyond our work, but we're the first that achieves the total query time trade-off that exists. It's a little confusing, kind of gets into the details of the lower bound, but I think the claim is true. Okay. So yeah, future work.
I guess my question is it trivial to also use a hash table in the previous paper to also get it to be tight? Like, I mean, you don't, I guess like you are saying, you cannot store it in a hash table because they are keys. They are like just PRF keys.
No, you can. You can use the hash table. The hash table technique is actually, it costs large space storage, so you cannot do it.
Did you get that?
Yeah. I guess the reason is because like you are storing a key for each set, right? So you can, that's why you enumerate all of them.
Yeah.
I see. Yeah, that seems very nice.
Yeah, I think so too. Yeah, so I'm interested in other applications of IPRFs and also how to get like these works that rely on puncturing. So the problem with puncturing is that you really do need a key per hint because you're puncturing out an element of that hint. And so it's not clear. You can't do this initial transformation where we have like a block, a key per block. For the people who are familiar with puncturing, that's kind of one big issue in trying to, like, our techniques definitely do, even if you had a puncturable IPRF, you can't use our techniques. But that's pretty much it. Thanks. Happy to take questions.
So I wonder why you guys don't do implementation? Because I think this game is pretty clean. And there's no like hidden details maybe.
That's a good question. I don't think there are any hidden details, right? Because both the prior schemes do implementation, right? I think we don't do implementation because we use a small domain PRP.
Oh, so that's very hard to implement, or
it's not very hard to implement. I think it just won't, it'll be slower in practice.
So in terms of efficiency, it's going to be like contra efficiency. It's not like good enough.
Yeah, we didn't run it.
I guess
Worse.
we had an implementation earlier. Maybe you can. I don't know if the code you can find it online, but I can dig around potentially. But ours is not asymptotically optimal, but it's practically fast because for small domain PRP, it's not clear whether those asymptotically optimal schemes are faster actually because n is small.
Yeah, wait, which I don't know which domain PRP you're talking about, but we need full
my co-author implemented this thing called fast PRP, but it's like square root n cost. It's not polylog, but it actually it's very fast for small n.
But I think the problem with fast PRP, I think we looked at that and it doesn't provide full domain security. And we need a small domain PRP that has full domain security.
What is full domain security? It's like
we need to be secure against an adversary who can see every input. Or who's allowed to query every single input to the PRP.
I see. What about those
good.
like swap or not shuffle? Like do those provide full domain security?
Yeah, so there's the paper we cite, I think, is the sometimes recurse shuffle, which is along that line of work. And it does provide full domain security. So like it exists and it's still like log in, it's like some polylog time with like not super concrete upper bounds, but I don't think it's
I thought the swap or not shuffle is very simple. It should be very simple to implement too.
It is very simple to implement. I just don't think it's faster. That like I think if we ran it, I'm skeptical that our scheme would practically be more efficient until you got to very large database sizes for like compared to piano or compared to MIR.
So
because you are comparing with square root, because like if you just do a linear scan, it's just square root. I see.
Like if you have a gigabyte of data or you have like 1 million elements, then scanning, like doing 1,000 SHA calls is going to be really fast versus like a small domain PRP. Like just practical efficiency. So it is kind of an asymptotic claim that we care about. And although like it's interesting to try to implement it because it's not like this is horribly inefficient. We're not using like LWE or like crazy puncturing. It's just probably for like the size of thing that you would be testing on, it's probably not going to be faster, but it won't be super slow.
So I guess one interesting open problems that can you remove that PRP in the construction of PIR? Like can you just only relying on like existing PRF to do this?
That's an interesting open problem. Yes, I suspect you can't.
Okay.
I don't have really strong arguments why you can't, but
wait, what do you mean? Of course you can. I mean, like this PRP, you can expand it, right? Like maybe you can get rid of some polylog factors if you expand everything out.
Oh, he was saying get rid of the PRP in the construction. So like construct an IPRF directly from SHA without.
Yeah, that's what I'm saying. Like because those PRP you can.
Oh, she's saying expand it out.
PRPs are very simple.
They use an underlying PRF. Yes, that's true. That's true.
Yeah, you can expand everything out and see whether you can get rid of some polylog factors.
Yeah, I guess practically like a more practically efficient IPRF is an open problem. Although, yeah, I think you'd have to find more applications to try to motivate that line of work first. And there may be other interesting applications theoretically before you have like.
Maybe if you can get it to log n rather than polylog n, it'll be faster than square root n.
Yeah, or maybe we just have databases that are so big that the asymptotics kick in. Right.
Okay, then no more questions. Thank the speaker.